from this surface to this surface, or vice versa, by doing something fairly simple. I took this handle and I slid it over this handle. Right? The handle slide this handle over that handle. So there's a canonical homeomorphism from here to here, gotten by doing that handle slide. So this is what we call an arc slide. There's a canonical homeomorphism associated with that arc slide. So, in fact, these arc slides, these set of arc slide homeomorphisms generate the mapping class groupoid. Not the mapping class group, because these govern between different surfaces. It doesn't make any sense. It's not set enough. You can't say that it's generates the mapping class group because the surface is different. But they generate this group. Those are really canonical looking set of generators, right? Like that's a really natural looking object. So, it turns out, through some sort of magic, so I'll explain. So, we can and will compute CF DD hat for these generators.
When you say that they generate the groupoid, does that mean that they generate all the maps between?
Yeah, that's right. So if that means that that's right. So it means that any morphism you can factor as a composition of these morphisms. That's right. That's right. Good. Okay. So the next thing I want to talk about, is going to take most of the rest of the time, is I want to talk about computing CFDD hat for an arc slide. How do you do it? There's a somewhat simpler case that has essentially all of the main features of this, and I'm going to talk about that case, and I want to focus on that case instead. That's the identity map. So slightly easier, but only slightly easier. CFDD hat of the mapping class, so the mapping sort of identity, which is just CFDD hat of f of z times 0. So we draw you a bordered Hagar diagram for the identity map. Maybe we use a split coordinate circle. There's a Hagar diagram for the identity cognitism. That should look sort of plausible if I glue this onto some bordered Hagar diagram. I can just use these blue circles and betas to destabilize these alpha arcs, at which point I'm left with exactly the same alpha arcs that I started with. So this acts by the identity if you glue it. This in fact represents the identity cognitism. Let's study this diagram a bit. So the first thing I want to understand is the generators. So let's mark a generator. Then chosen how do we evaluate the generator? I chose for each of the blue circles, I made a choice of left or right. I wasn't put the point on the left or on the right. There's some associated idempotence to this that comes from looking at the alpha arcs not occupied with vector. So let's draw these dashed. So here's the associated idempotent to this generator on the left and on the right. So there's the idempotent associated to this generator. You notice that I see each idempotent on the left exactly once because, again, for each blue circle I pick left or right, and the dashed lines are the ones I pick right. So there's a correspondence between idempotents on the left and generators. And the idempotent on the right is complementary to the idempotent on the left. Right? This is the opposite. I've got dashed lines in places here that I don't have dashed lines there. So the generators are in correspondence to pairs I, J of complementary idempotents. In L associated C, that's the L associated points. Okay. So good start. Let's think about the differential. Here's a sort of region that could contribute to differential. In fact, it does. It's a hexagon, and as a hexagon, it's going to always contribute to differential. It contributes to differential with the dot arrow, the empty circle is the solid circle. So here's a domain contributing to the differential. They have the same multiplicities on the left and the right. Notice I've got multiplicity 1 there and 1 here, and 0 everywhere else. So the multiplicity are the same on the two sides. So the same multiplicity on the left and the right. So, if boundaries of generator X, which then corresponds to the complement pair I, J, contains a term of the form A tensor A prime tensor X I prime J prime, then the support of A, the multiplicities of A on the left agree with the multiplicities of A on the right. Multiplicities of A on the left are equal to the multiplicities of A prime on the right. So let's let the diagonal algebra, so let's say P, be the set of elements, so generated by the set of elements A tensor A prime in A and Z, tensor A of minus Z, such that the multiplicities of A are equal to multiplicities of A prime. This is what we call the diagonal algebra. So, I haven't talked about gradings in these lectures because the gradings in order for somewhat confusing. It would have taken an extra day to talk about. We only have patience for so many days. So, I need to use them a little bit now. Consider the gradings. Well, there's a z grading on this diagonal algebra such that, which is compatible with the differential on CFD in excuse me. Sorry. Compatible with the differential on CFD of it, and such that the only terms in grading -1 have the form of the form A of rho tensor A prime rho. So where rho is a single chord. So these are the things that look like this. They're just a single moving strand and possibly some horizontal strands overlap. Okay. So plane here. The differential, so let's let A be the sum over chords rho of A of rho tensor A prime of rho. Then the differential of x I j is the sum over xjk of I tensor j times A times xjk. What am I saying? I said here that the only terms that can show up in the differential are these chords of this form. And here I'm saying that every chord shows up. Let's see if we can find an example in that diagram. So, we erase this little domain, but come back to it. Great. So, here's a term that shows up in D of this algebra element. Is that backwards? Yes. Sorry, just a second. We can try to say something that's true. Great. Sorry. Okay. And it's ending on C, so I don't have this dash thing. But I do have this one. And this is ending on this, so I don't have this dash one, but I do have this one. Okay. it's long chord, it's a pair of chords on the two sides. Why is this one upside down? Because I'm looking at A minus Z, remember? So something got itself orientation first, this one. Okay. Let's think just briefly in order to convince you that there's something to prove here. Let's think about the holomorphic curve that might exist to generally cause this component to this term that appear in the differential. I mean, it does exist to cause this term to appear in the differential, as I'm saying the term contributes. So it's containing this region. It's also containing this region, which the top here goes along there. It's containing this region, also that one, and also this one, and also this one, and here, and here, and the top here is part of there, so also that. Okay, that even has quarters in the places I'm playing, I think. That's good. What is this? This is genus 1, 2, another annulus component, another annulus there. So this is genus whatever, something like 2 with 3 boundary components, something like that. This is way far from a disk. If you ever try to compute differentials by hand for Hagar-Föhr homology, you would not want to compute this by hand. So this is probably, this domain is, I'm going to go out on a limb and say impossible to compute by hand. To verify. Okay. It's a very complicated looking holomorphic curve. So there's some content here, I'll tell you. So not a direct computation. How do I do it then? In fact, the answer is false. So this crash. Sorry, the board was so nice before I got it. Great. This follows from two things. One, check it for short chords. So it's true for short chords. What do I mean by short? I mean the ones that just look like the domains that just look like this. Well, there's nothing in between, so these minimum possible choices. Because, well, they're hexagons, and so it's easy to check that the holomorphic curve exists, so because they're hexagons. Okay, so those do appear in the differential. Okay, so short chords do appear in the differential. And then the second step is that, well, we use induction, we prove it by induction on the length, using the fact that boundary squared is equal to 0. So, great. Let me do an example of that induction for you. Let's do a short example because I want to show, let's say this is a length 2 pair. So, here I've got, this is a little piece of that diagram. That this pair of chords comes up with a differential. Okay. Does this come up with a differential? So this is in d of x. Well, let's call this element, so let's call this rho. If so, then d squared x would contain this term, right? because I can differentiate this algebra. But there's, whoops, I'm drawing backwards. But there's a unique way to factor this, there's a unique other term that contributes this to d squared x. So this is also from this multiplied by this. So put some tensor products. So this product gives me exactly that element. Right? See, put them together. And these are both short chords. These do appear in boundary by an inductive hypothesis. The only thing that this can cancel with a d squared is this to them. So d squared equals 0 implies that this adds to a pair of d. Okay, so that argument's written a little more formally in the notes, and still more formally still in a paper. But that's the gist of the argument. So we use induction use induction d squared equals 0. See that the short chords plus this builds up everything. Okay. So let's recap. We computed CFDD of the identity diagram. If you were TQFT-ish, you might have thought CFDD of the identity diagram was going to be the algebra, but you would have been wrong. It's this thing. What do we use to compute CFDD of the identity diagram? We use the fact that we understood the generators, we use some of the gradings, and we use the fact that we need these short chords contributed. You probably know the short chords contribute for a sort of abstract reason. You probably know that the short chords contribute for a sort of abstract reason, which is gluing on the identity carbonylism, or actually any mapping, so there's an invertible operation. So the operation on modules has to be an invertible operation also. And if these short chords didn't contribute, you could probably find a hookup of modules so that this wasn't an invertible operation. So this little bit of analysis that came in and checking these hexagons contributed, probably you could actually short circuit the talk and get by sort of formal properties of the subject. And the gradients and sort of formal properties too. Okay, arc slides. So next, we warmed up, right? Next, arc slides. So a Hagar diagram for an arc slide looks very similar to a Hagar diagram for identity. Let's start with the diagram for identity, in fact. So it looks like a Hagar diagram thing, and something to do with, let's say I want to do the arc slides thing out earlier. I think that was sliding this foot over this foot. So let's just do that of sliding this foot over that foot. So what happens if I do that? I get this foot slide. This now goes around to there. Comes at the bottom of C here. Great. So there's a diagram for an arc slide. This is a diagram for arc slide. One kind comes again from looking at these complementary idempotents, so that it's complementary idempotents. That's if I don't use this point, so if I use this point or that point. There's another kind where I use this point. So, for example, this, this. So that would correspond to this pair, and this pair, and this pair, and this pair. So it's almost complementary, but it's not quite complementary with the C. So generators are now near complementary pairs of idempodes. I haven't defined that, but you could come up with a definition if you wanted to. And now it turns out that the differential is the sum of all near chords. Okay, what's a near chord? Well, there are basically 6 types. They're listed here. I'm not going to list all of them for you on the board because you don't enjoy it much. You draw that much, I assume. Let me point out a couple of them, like one of them that you haven't seen in the other case. Here's a domain. That's a disk, so that contributes a differential, and it just contributes this little gadget over there, which I'm supposed to be drawing upside down. Okay, so you can then get some more by extending this one and so on. So this is again, the proof is the same idea, so proof is the same ideas as before, nearly. So it's nearly the same as before. So how does that go? You define a near diagonal algebra. You see that there's a Z gradient on the near diagonal algebra. You see that short near chords exist by using a direct union. You see the remaining near chords exist by and Dutch or using d squared equals 0. So it's the same as before, so we had a little near before it. Great. Okay. I think I've got 5 minutes. It's maybe not so much fun watching do these sort of details of this on the board, so maybe I say something slightly different in the last 5 minutes. What about 4 manifolds? So, carbon maps on HF. So if you have a 4-manifold, 4-dimensional cobordism from HF hat of Y1 to, Y1 to Y2, then it gives you a map. So from HF hat of Y1 to HF hat of Y2. Suppose I want to compute those maps. I just told you how to compute HF hat of Y1. So to compute this, how's the map defined? Well, the map is defined in 3 stages. You decompose W as W3 composed with W2 composed with W1, where Wi is high-angle additions. You get by gluing on 1 handles, 2 handles, and 3 handles. So I start with Y1 with 0, 1 plus Y1, and I glue on 1 handles and 2 handles and 3 handles. There are 2 things that are So gluing on one handles, so W1, it just takes Y1 and it replaces it with Y1 plain subplot to S2 times S1. S2 times S1. The map here is sort of standard, so it's a map from HF hat of Y1 to this is HF hat of this, which is HF hat of Y1, tensor with the homology of the K torus. And this just sends X to X, tensor with the top dimensional top gradient generator, the homology of the torus. Okay. So that's easy to compute directly, at least if you've already given this decomposition on the right, sort of with respect to this decomposition on the right. Y2, this is the interesting one. So this corresponds to surgery on a wing. Well, let's take our wing that we're doing surgery on. Let's connect up the components so that I've got actually a graph whose complement is a handle body. So let's take, L, so think L, and then L, let's call this thing, let's call this Y. 2. Sorry, probably 2. Embed L as the sum as in a handle body for a Hagar splitting of Y2 in a standard way. Then FW2 is a map from CFD so we've got Y2 is H1 union boundary H2. L sits inside H2. And I've got, so CF hat of Y2 is more from CFD hat of H1 to the CFD hat of H2. Let's say that W2 goes from Y2 to Y3. Y3 is more from CFD hat H1 to CFD hat some other handle body H2 or H2 prime gotten by performing surgery on this standardly embedded link inside H2. Well, how do I get a map from here to here? I just need either a map from CFD of H2 to CFD of H2 prime. So this comes from composing with a standard map. Ooh, I thought. Well, better. With a standard map from CFD of H2 to CFD of H2 prime. The standard map comes from, so this actually is basically one of the maps that shows up in the surgery exact triangles. This is just a tensor product of maps for the surgery exact triangle. And there's one more ingredient which I have to be able to go from Y2 is this connect sum, but the decomposition I'm using here and the decomposition up there are different. I have to be able to compute that continuation map. So the last ingredient is that having it written this way, there are no automorphisms of the standard handle body in Hagar for topology. So that is ordered for topology. So you can compute the continuation maps because they're actually unique map that respects this decomposition. So that's the last sort of tricky ingredient. That also computes the format for the variables. Okay, thanks for listening.
or comments? Yes.
Out of the minus or plus theories.
How about the minus and plus theories? So I deserve that because I started talking about four manifolds. If you want to get interesting information about four manifolds, I'm going to be talking about one very Taylor homology, which is HF hat. If you want interesting four-dimensional information, you need to deal with the fancier versions, which are HF plus and HF minus. There is currently not a bordered third story for HF plus and HF minus. Maybe that will change, but currently there's not a bordered third theory for HF plus and HF minus. I don't particularly recommend that as a problem to work on, but that's the state of affairs.
So how does the complexity of this algorithm work?
Great. So the question is, there's already, great, I should have said that, right? So I'm very glad you asked. I should have mentioned, this is not the first algorithm for computing HF hat of a free manifold. The first algorithm is doing the Sarkar-Wen. So the first algorithm to compute HF hat of a free manifold is due to Shin Sarkar and Jiajun Wang. It's very different. You produce a particular kind of Hagar diagram, which is they call a nice diagram, and you can directly compute the differential there. The original algorithm is somewhat inefficient. I had some summer students, one of whom was in the audience, who sort of studied it, and it seemed that if I remember right, the running time was something like quadruply exponential. So the original Sarkar-Wen algorithm is pretty bad. I mean, the number of generators you get is something like quadruply exponential. You can improve that down to merely sort of factorial to the n to the n log n or something, I think. So you can improve that down to something, maybe it's a little worse than that. So you can improve that, I've forgotten exactly what it is, but you can improve that to something significantly better by making some minor changes. There's a paper of Peter and Zoltan Andras that gives another variant that I think is also faster than the original running time. But I don't know that someone's thought out the computational complexity there. Somebody could do that actually. The question is about counting the number of generators you get when you do these modifications to a diagram, basically. And like, this is something we should be able, like the human race should be able to understand the answer to this question. This is also, the size of the algebra grows exponentially with the genus. So the behavior of this algorithm is a little bit different. In practice, where you have to analyze the efficiency either. Somebody should do that. Human race should, okay. The time that gets inefficient is when the genus of the Hagar serves you need goes up. So in practice, it works pretty well for genus 2, and it works barely for genus 3, and above genus 3, it doesn't work at all with the current implementation. That could be improved by doing some more mathematics. It's implemented, you can run it to do things like branch level covers and knots. So I implemented it in Python, was ported to C and improved by Bohua Shah, who's a student of Peter and Zoltan's. His version that he used to compute branch level covers like 17 and 19 crossing knots. So it's fairly large, fairly complicated thing. So it actually runs in useful time. I don't think any version of the Sarkar-Wen algorithm has ever been ported to a computer in a way that runs on anything. So in that sense, it's a little bit better. Let me toot my own horn a little bit more. Well, so it's not bad to do that. There are other nice things about their algorithm. You can use it to prove things. For example, Andras Juhas used it to prove the decomposition theorem for sutured phenomenology, which then has other results. So theory is actually nice for proving it, even though it's not so useful in practice. Second thing I was going to say. Oh yeah. For this sort of thing, it's natural enough that if you want to do a particular computation, you can often combine using a computer and working by hand. So Adam Levine did that, and it's not in this setting, but it's not a different order for a setting, and you can do it there. Then you could break your manifold into sort of into pieces, and you do some thinking work to compute either of those pieces, and you can do some computer work to glue them together. So it adapts itself if you have particular computations doing some more work and getting more out of it, because there are other decompositions of free manifolds other than Hagar splittings, and if you break them up into, you have to compute something for the pieces that takes some intellectual work, and then you have a faster algorithm. So you can always make it faster by doing more intellectual work. So it's sort of that was a long answer. Sorry.
Okay, this was the last lecture by Robert, so let's thank you.